You guys having any issues on the homework with confidence intervals, anything like that? Feel good about that? So I'll put up a practice test on today, Monday. I was gonna say on Monday, but that's today. So I'll get you a practice test this afternoon or by tonight at the latest. If you don't see it by 4 or 5, that means it's not coming until probably midnight, but it'll get there. I can get it. Whatever I get done by 4 is all I get done until like 9 or 10, because then I have to take care of my children and stuff. So they apparently want dinner and pajamas or something. I don't know. So anyways, but I'll get it out there for you. And then we'll take the test on Thursday. It'll be in class. It'll be over chapters 9 and 10. Confidence intervals, and then hypothesis testing, which we started talking about on Thursday. We're going to get some good examples today, so it's not just all, theoretical stuff. We'll actually figure out how to make those decisions, and then we'll do some. All right. All good? Sound good? Everybody happy? We only have 10 more days of class.
Seriously?
Yeah. 4 this week, and 2 next week. Oh, yeah, only 2 next week, and then 4 the week after that. And then finals week. Yeah. Thanksgiving next week. So, yeah. And since my in-laws were in town, we had Thanksgiving dinner last weekend, and I get it again on Thanksgiving. So, I get 2 Thanksgiving dinners, so I'm pretty pumped about that. All right. Not relevant to statistics, but it made me happy. Yeah.
So, does that mean we'll be in class to review for the final?
Yeah. What do you mean?
After this test, is there new material? Or is it
Yes.
There's new material.
Yeah, I got one other thing I want to cover after the chapter 9 and 10. We got chapter something, 11 or 12, I can't remember which one. Yeah. So we're going to cover some new material on Monday, Tuesday, and maybe into Monday, Tuesday of the next week. And then we'll be reviewing for the final Wednesday, Thursday of the last week class.
And then no class.
Then there's no class. Yeah, then you have finals week. Monday is a dead day, so it's just a study day. And then finals are Tuesday, Wednesday, Thursday.
Are you going to be
Ours.
on campus Monday in case, questions?
Yeah.
Okay.
Yeah, I don't know what I'm going to do, but I'll be around. I don't know if I'll be at Phi Theta. Phi Theta Kappa does a study day every Monday, or like that dead day of every quarter. Sometimes it gets a little loud over there. So I may end up just doing something over here in the math center. I might be around over there that day instead, but it's a little quieter. Okay, so what we were talking about last time is this idea of hypothesis tests. So we're testing claims, and there's something called a null hypothesis, which is the claim, and then there's an alternative hypothesis, which is kind of what you think could be true otherwise, right? And we talked a little bit about type 1 and type 2 errors. Sometimes type 1 errors are really bad, sometimes type 2 errors are worse. And the way we decide how to pick our alpha level is based on which one we think is worse. So I think at the end I gave you a little kind of summary. So if a type 1 error is worse, you decide, then you would want to pick a low alpha level because your alpha level controls that type 1 error. So pick a low alpha of maybe 1% or lower. If you think a type 2 error is worse, then you say, okay, don't want to do that, so I'd rather make a type 1 error, so make that alpha level a little higher. And that's what we decide. And we decide those in advance. If you don't really care and you think they're both bad, but neither one's worse than the other, we typically just default to an alpha level of 5%. Okay? All right, cool. I thought that was a pint of Haagen-Dazs that you're eating. I was like, dang, dude, ice cream in class, that's an awesome idea. How can you make stats any better? Maybe ice cream. Maybe ice cream. Okay, so then we got into this conversation about when you actually decide to reject. Okay, so we were looking at this example with, the car claiming it gets a certain mileage and we think maybe it gets less. So you go out and you test some samples, and if it was a little lower, you'd say, yeah, whatever, maybe I just got a couple bad cars or maybe I'm a bad driver. It gets a little lower, now you're getting suspicious. Eventually that average is going to get so low that you're going to say, nope, I don't believe you anymore. I'm going to reject your claim, and I'm going to go with some alternate belief. So we had to decide how to make the cutoff. So I said, well, what we're going to do then is what we're going to use the central limit theorem, and here's how we're going to do it. All right, so let's just think about the example of a proportion. Okay, and we'll come back to the mean in a little bit. So let's say we're looking at a test like this. So they claim the true percent is some value. We think the truth could actually be maybe something bigger than that, right? Okay. So we say, all right, now the central limit theorem tells us, though, it tells us that if n is large enough, and I think, what's the cutoff they use? Like n times p times 1 minus p is greater than or equal to, do we use 10 in this book? Is that the cutoff in this book? I think it's 10. Something like that. So if n is large enough, then p hat is approximately normal. So sample proportion, remember we use that symbol p hat. So what is it centered around? What is the sample proportion centered around? Sometimes it's a little more, sometimes a little less, but it's always centered around what?
Can you repeat that?
So the sample proportion, right? Sometimes you're going to overestimate, sometimes you're going to underestimate, but it's always centered right around the what? So p hat is a sample proportion. It's always centered around the what? Well, not the mean, because we're talking about proportions. So go back to the central limit there. It's unbiased. It's always centered around the just start throwing them out there. Placebo, stratified, right, no. It's always centered around, it's centered around the true proportion, right? It's always centered around the true proportion. Because remember, there's this idea, for the population, there is some true proportion, but for our samples, all we have is a p hat. But the sample proportion p hat, it's always close to p, right? The true proportion. Now, remember though, when you go into like a trial, what's the assumption you work under until you can prove otherwise? You always are supposed to work under what assumption? Not guilty, right? So in a hypothesis test, we always assume that H naught is true until we can prove otherwise. So we do hypothesis tests just like we do trials by jury. Someone makes a claim and we give them the benefit of the doubt and assume they're telling the truth until we can prove otherwise. Okay? So if they're telling the truth, then that means that P naught is the true proportion until we can prove otherwise. Okay? That P0. All right. So that means that our sample proportion is going to be centered around the true proportion, P naught. So if they were telling the truth, our sample proportion should be pretty close to that value that they're claiming. And it should have a standard deviation of this. Right? So if they're telling the truth. If they're telling the truth, then we should see sample proportions that are centered around their claim. You know, sometimes we'll see sample proportions a little higher, sometimes a little lower, but it should always be right around their claim. And it'll have this standard deviation because we know that from the central limit theorem. All right. So that means, I'm going to draw you a picture. We're going to draw a normal distribution now. Okay? Everybody here? You okay? Caught up? All right. So we're going to a normal distribution. That means that p hat, so this is going back to sort of chapter 7 or something. P hat comes from this normal distribution that's centered around P0. You know, sometimes if they're assuming H naught is true. So assuming they're telling the truth, our sample proportion comes somewhere off this normal distribution. Most of the time it should be down here close to P0. Sometimes it's going to be a little bigger, sometimes it's going to be a little lower, right? So what we're testing here, remember, our test here is that they're claiming it's equal to P0. We think maybe the truth is something greater than P0, right? So if you see P hat, say here, or maybe here, or maybe here, are you going to reject their claim? You know, something really close to the mean. You're not, right? But eventually, that P hat is going to get so big, right, that you're going to make a cutoff. All right? You're going to make a cutoff here. And as soon as P hat exceeds that value, as soon as your P hat gets big enough, then you're going to start saying, look, this is getting pretty far away from your claim. I'm getting pretty skeptical. I don't really believe you're telling the truth anymore. Okay? So up here, this area here, this is what we call the rejection region. The rejection region. So eventually it's going to go past that cutoff, and we're going to reject the null hypothesis. Of course, down here, then, everything down here we're going to accept, right? Now, remember, at the beginning, we took our alpha level and we set it in advance. Right? And what is our alpha level? It's the probability of a type 1 error. What is a type 1 error? You commit a type 1 error when you do what? That's type 2, actually. Yeah. When you reject when you shouldn't. You reject their claim and you shouldn't have, right? So just looking at this picture, say they are telling the truth, right? And you establish a cutoff. Sometimes you really are, just because of random chance, sometimes you're going to get P hats up here in this rejection region, even if they were telling the truth, right? So in this rejection region, you're going to say, well, it's really far away from their claim. I'm going to reject their claim, and in fact, they were telling the truth. Well, you just committed a type 1 error. Well, you only want to do that alpha % of the time, so we bound it. So what we do is we basically say, okay, I'm willing to commit that error, alpha % of the time. So we choose our cutoff so that our cutoff leaves the probability above it as alpha. Okay? And so what we're going to pick, our cutoff, is we can actually calculate Z alpha, can't we? We know how to do that. So say like our alpha level was 5%. Could we find the Z value such that 5% was above using the Z table? We could, right? All right. So we're going to choose our cutoff, and then we're going to use what we call a test statistic, because we know that if you take P hat minus the mean divided by the standard deviation, that's going to be a Z value. And so in this case, the claim is P0, and the standard deviation is P times 1 minus P over N. So this is going to be our test statistic. It's going to be a Z value. This is going to be our cutoff. It's going to be Z alpha. And then we're going to take our sample, we're going to calculate our Z value, and then we're going to see, did that Z value exceed the threshold, or did it not exceed the threshold? If it exceeded the threshold, we say, nope, don't believe you, reject. If it didn't pass it, then we say, okay, you could be telling the truth, I'll take your word for it. All right? So, I'll give you a review here. So this is how we're going to do a hypothesis test about proportions. We'll get to the mean in a second. The mean is trickier. Same reason that the confidence interval for mean is trickier. We have to use that t value. Makes life harder. But for proportions, nice and easy, we'll use these. So hypothesis test about proportions. The first step is you state your hypothesis test. So that's that H0, H1. Okay? Then you're going to use your alpha level. Alpha level. To establish a cutoff. And sometimes we call that cutoff a critical value. I think your book might use that terminology. It's like saying this is the critical value where you can't go past. Okay. Then you're going to calculate your test statistic. And it's a statistic because it comes from the it comes from the sample. So it's going to be p hat minus p0 all over the square root z0, 1 minus p0 over n. So you got your hypothesis. You know now what the cutoff is based on your alpha level. You got your test statistic. Now you just decide, right? If z is in the rejection region, then you reject the null hypothesis. If it's not, don't. Okay, sounds complicated, but in practice we're going to find it's not too bad. Just takes a little getting used to. All right, so you want to do one?
Not really.
Not really? Well, other people would like to, so we're going to do one anyways. That's okay. Honesty is okay sometimes.
I'm just looking at it, not a whole lot I would want to do.
All right, so let's try one. All right, so let's say we're looking at pass rates, and so I gave you an example where maybe we're trying something out in Math 84. So let's say that previous pass rates in our Math 84 classes are about 65%. All right? So 65% historically have passed Math 84 over the past however many years or something. So maybe you think that a new program will be better. So you decide to try something new, and you say, I'm going to try something new. I think it's going to be better than the old way we were doing it. I think it's going to improve things. Okay. So you go out and maybe you do a sample, and you do some of your sections a new way, some of your sections the old way. And let's say that over the course of a year, 180 students take the new approach. And 130 pass. All right, so then my question is there evidence, and we'll say at the 0.05 level. Is there evidence that the new program is effective? All right. So you put 180 students in there, 130 of them pass. And now we want to know. So first step is I need to set up my hypothesis test. So what is my null? What should be my null and alternative hypothesis? Remember, we're talking about a proportion because we're talking percentages. The null hypothesis is always equal to. So you can at least know that up front. What should we probably set our null hypothesis to?
0.65.
Yeah, we'll say, you know what? I'm just going to assume that it doesn't do anything. Let's just assume it's ineffective and that my students are going to do exactly like all the other students are doing in all the other programs. It's going to be 65%. What do we hope or believe might be true? It's better, so probably what? We think the alternative would be maybe what? Greater than, less than, or not equal to? Greater than. So we'll assume it's going to be the same as everything else. We're hoping to show that our percentages are greater than 65%. And then now we got some data. So here's that step one, right? That's the hypothesis test. Now what we need to do is we need to go get a critical value or a cutoff. So our alternative here is P is greater than P0, right? So since my alternative is going to be greater than, we're going to reject when we see things that are too big, okay? Well, so our cutoff is going to be up here, and we want to do it so that we only make a mistake 5% of the time. So we're going to allow ourselves 5% up here, right? Because that was our alpha level. So then our critical value is going to be z sub 0.05. It's going to be the z value where 5% is above. And if you look that up, it's going to be, that's the same as the 90% confidence interval value, I think. You guys got z tables on you by chance? Attached to your other exam or something like that? Or did you turn them back in after I gave you your exam?
1.96.
Well, that would be z sub 0.025. It would be the same as a 90% confidence interval cutoff.
Oh.
Because remember, in a confidence interval, you do alpha over 2. So if your alpha was 10%, 5% goes down, 5% goes up.
1.645?
Yeah, I think so. I'll pull up the Z table just so we can see it anyways. Yeah, I usually find it off the negative side. But so we're looking for basically, if you look at this, we're looking for the 5th percentile, right? Basically, or the 95th percentile. So we put all our alpha, all our error up in the top because that's where we want to reject that. So 5% is the cutoff. If we go to our Z table, go to the 5th percentile on the negative side, happens right between here and here. So it's negative 1.64, negative 1.65, you average them. So it's negative 1.645. That'd be your cutoff on the bottom. Of course, we're on the positive side. Okay. So you get it off your Z table, and you say, okay, so this is my cutoff. So that means up here, this is my rejection region, right? So up there, I'll reject. If it's anywhere down here, I'll fail to reject. Right? So if my test statistic goes above 1.645, I'm going to reject the null hypothesis. If it doesn't, I'm not. All right.
I have a question.
Yes.
I don't know how you found it.
That value. So if 5% is right here, how much would have to be below it? 95%. So go to the positive side of your Z table and find the 95th percentile. Where do you hit 0.95? What's the Z score? So remember, you're looking inside the table.
Oh, okay.
Remember, yeah. So for percentiles, you're looking for 0.95 inside the table. So if you did it from the positive side, I'll go to the next page. Oh, okay, cool, dude, chill. Whoa. Okay. Ah. What the heck? It's there. I don't want to. I don't know. My computer's being weird. But I do it on the negative side. So it's rather than look at the 95th percentile, I just look at the 5th percentile, and then I use the positive z-score. All right. All right. So we got our hypothesis. We got our critical value in our rejection region. Now all we got to do is we just got to go get that test statistic. All right. So the z-value we're going to use is going to be p hat minus the null hypothesis all over the square root of p0 times 1 minus p0 over n. All right. Looks like a mess, but it's not that bad. By the way, what is our p hat? What is our sample proportion of students who passed in our new program?
0.65?
That was our old program. Yeah, in our program, 130 out of 180 passed. And what does that come out to be? Someone said it. Is it 0.72? So it looks like our program was effective. Now, just because our percentage is higher, though, does that necessarily mean our program's effective? Not necessarily, because that could just be random chance, right? We may have just happened to have gotten 180 students in those sections of classes that just happened to be more successful. It might not actually be due to our program. That's why we do a hypothesis test. All right, so now we're going to calculate our z-value. So z is going to be 0.72, that's our sample proportion, minus the null hypothesis, which was 65%. And then our downstairs is going to be that 0.65 times 1 minus 0.65 all over our sample size, which was 180. Okay. So that's going to be upstairs, that's going to leave you with basically, what, 7%? And then downstairs, whatever that is, I don't really know. Somebody want to help me out here? I'll try it on mine. You try it on yours. Let's see if we can get a consensus. So 65% times 35% divided by 180. Take the square root of that. I get 0.03555555 something. Something like point. Whoa, that was cool. Oh, 0.3555 something something something. And then if you divide those, what do you get? About 2 something? 2.7 divided by that. What's your z statistic? Is it 1.97? 1.97? Can I get a consensus? Okay, I got some other people saying that. So it's about 1.97. So what does that mean? This tells us that our p hat is 1.97 standard deviations above average if H naught is true. Is that common? Would that be something you would see commonly? 2 standard deviations above average is getting up there. So now compare it to our cutoff, right? So in step 4, we have to make an actual decision. So we established a cutoff, 1.645. Where is our z-score? Yeah. Our z-score is 1.97. It's in the rejection region. So what should we do? Yep. So z is in the rejection region. So that means we should reject the null hypothesis. Okay, so let's back up. This was our hypothesis test, right? We were saying let's assume it's 65%. Maybe we can show it's better. We wanted to do it at a 5% alpha level, so we put all that up at our top tail since we wanted it to reject when it was big enough. So we got a cutoff from the z table. It said if we get z scores bigger than that, then we're going to reject. That means as long as we make that our cutoff, we're only going to make a type 1 error 5% of the time or less. Okay, which we're willing to do because we set our alpha level there. We calculated our actual test statistic. It was a 1.97. That exceeded that cutoff. So then we should reject our null hypothesis. Now, what does that actually mean? How do you interpret that? Okay, so maybe I should add an extra step here. You know, there really should be a fifth step, right? Because if you take this result to a non-statistician, say like an administrator or something who maybe doesn't do a lot of statistics, and say, oh, here was my null hypothesis, here's my alternate hypothesis, I rejected it, so there you go, right? But what does that actually mean? What are we actually saying now? So the null was that it was 65%. The alternative was that we thought maybe it was more than that, and our decision was to reject H naught. So then what are we actually saying? We're saying that there's evidence to reject that null hypothesis, which means we believe what's true? We're thinking maybe it looks like there's enough evidence to suggest that the alternative is true, which means practically what in the case of this particular problem? It's a 50-50 chance. So which one is it?
Lands up above, it would be more effective.
Okay, so the null hypothesis, is the null hypothesis ineffective or effective?
The null is ineffective.
Yeah, the null hypothesis is basically saying no effect, right? It's because historically people are passing at 65% anyways. So if our program is making people pass at 65%, well, that's cool. We have this new way of doing it, but it's not really doing anything. It's just like everybody ever before was doing. So then our alternative is basically that it is effective, right? So if we reject the null hypothesis, which was basically no effect, then what we're saying is we're saying, nope, it looks like that's not true. It looks like there is some effect. Go ahead.
Okay, so pretty much what we just did we test like the new way or did we test the old way?
We tested a new way.
So, okay, but in real life, like, didn't we test, like, the thing was, like, with less people than have done it over the past, right? So, like,
180 people.
well, how many people have taken the class the other way?
That's right. Yeah, so it would be less. It is a smaller sample than the overall population.
Anyway, that just doesn't matter.
Well, so that's the thing. So the thing is that our test statistic takes into account the sample size, though. So like if you have really small samples, then it's going to be really hard to get a statistic big enough. So the bigger your sample size is, the easier it's going to be to see results. So since our test statistic takes into account that sample size, it's okay that we don't have a huge sample size. It is. Because our test statistic takes it into account. I mean, it's a good question. Yeah. So, I mean, can we actually say for sure that this is going to be effective if we roll it out to the population, like with 100% confidence? I don't think so. We can't. Because remember, in statistics, we can't ever be 100% confident in anything. But we are 95% confident, right? Because we set our alpha level to 5%. So we have some confidence. But you're right, the sample size can be an issue, but our test statistic does take that into account. So like if you only sampled like 4 people, then this would be a really bad idea. It also wouldn't meet this criteria right here that they set for proportions. So they want to make sure that your sample size is big enough. You're supposed to take the sample size times your proportion times 1 minus your proportion to see if it's big enough to even use the central limit theorem. Yeah, good question though. Yeah, but I mean it's unfortunate because the answer is really we can't be sure, but at least we have some confidence now. I don't know if that's a very satisfactory answer. Is that okay?
Yeah.
Yeah? All right. You could say no if it's not. Okay. Thinking about that though, you do have to be careful about how you really phrase this. Because think back to like a jury trial. Just because you convict someone of being guilty or say they're not guilty, does that actually mean they're guilty or not guilty? No, there's always room for error. So the way we would interpret this then is we would say something like at the say alpha equals 0.05 level, which by the way corresponds with about 95% confidence. Remember, our confidence and our alpha level are related that way. So at the alpha 0.05 level, or with 95% confidence, we would say there is enough evidence to suggest that pass rates in the new program exceed 65%. That's how we would phrase. So typically when we, just kind of like with confidence intervals, we have a really particular way we like to report them. With hypothesis tests, we also do. We report the alpha level. And then typically what we report is we report the alpha level we tested it at. And if there is or is not enough evidence to support the alternative. That's kind of a general rule. That's sort of how we typically report it. We say what alpha level did you do it at, and then did you have enough evidence for your alternative or not? Okay. In this case, since we rejected the null, which was no effect, that's saying that there was enough evidence for us to suggest that the new program produces pass rates that exceed 65%. Now, are we saying that the new program will produce pass rates of 72% if we roll it out to the entire population? No. We're not saying that 72% is the truth. We're not even really making any suggestion about what the truth could be. We could use a confidence interval maybe to do that. But what we are saying is that it looks like our new program exceeds the 65% current sort of status quo. So, yeah? Does that make sense? Kind of? Yeah? Kind of. What questions do we have? Okay, we'll do another example. I'll do another example. Any questions about this one particularly? All right. Hypothesis test, cutoff, z-score, decision. Then the hardest part is the interpretation. What are you actually saying? Right? That's the hardest part, I think. All right. Now, notice that in this case, our alternative was greater than. So we loaded up that whole entire alpha level up top, right, to get our cutoff. Now, it depends on your alpha. It depends on your alternative, how you get that cutoff. So I'm going to say cutoff based on your alternative. So if your alternative is greater than, you're going to handle it just like we did it. You're going to load up all your alpha up top. And then your Z alpha is going to be your cutoff. And you're going to reject when you get too big. Like that one. Now, if your alternative is less than, though, if your alternative is less than, you're not going to reject for big values. You're going to reject for small values. Right? So then, if your alternative is less than, you're going to load up all that alpha level down at the bottom. And your cutoff is going to be like a negative, is going to be the opposite, negative Z alpha. So your cutoff is going to be a negative Z score if your alternative is less than. So if your alternative is greater than, load all your alpha upstairs, get the positive Z cutoff. Your alternative is less than, load all your alpha downstairs, get the negative Z cutoff. The only time it gets kind of tricky is that case where your alternative is just strictly not equal to, then it gets a little weird. Because in a not equal to scenario, you don't have any idea going in which way you think it might go. You might reject if it gets too big, and you might reject if it gets too small. So you actually have to have two cutoffs, a lower cutoff and an upper cutoff. And but you don't want to sacrifice your alpha level. You want to retain your alpha level. So what do you think you should do with that alpha rather than loading it all on one side? What do you do? Yeah. You split it in half, and you put alpha over 2 down there and alpha over 2 down here. And then your rejection region is actually on both sides. You'll reject down here below z alpha over 2 and above z alpha over 2. So once we call these over here, these are what we call one-sided or like one-tail tests. So like a lower tail or an upper tail test, one-sided. And this is called a two-sided or a two-tailed test. So I think your book here, Homer, might mention those phrases, like a lower tail, upper tail, two-tailed test. All right. Okay. Let's do another example. Yeah? All right. Let's say you go let's say that we went into this Math 84 experiment. And we know previously the pass rates are 65%. Okay? And so maybe you go into this experiment and you have no idea how a new program will affect it. So you say, I'm implementing this new program. Honestly, I don't know what's going to happen. Maybe you don't have any control, and the state or some of the administration just comes in and says, here, we're changing it. This is the way we got to do it for some reason. And so you just implement it, and you have no idea if it's going to work. So you go out there, and you implement it in some pilot sections. And so in a year, maybe 200 students have taken it. And 120 pass. So by the way, what would the p-hat be in this case? Which is 60%? Is that right? So going into this, you don't really know. You're like, I don't know. I mean, maybe this new program could improve rates. Maybe it could hurt them. It looks like what's possible. It's possible that the rates have gone down. Now, just because these particular 200 students had a lower pass rate, though, does that necessarily mean that if you implement it college-wide that it's going to actually hurt rates? Not necessarily, because what could be true? What could have happened in your sample? What could be true about those 200 students that you ended up having in the new program? Just by random chance? So these students did worse than the overall average, but what could be the case? Do you think all classes have the same pass rates? Do you think every stats class has the same pass rate? No, not necessarily, right? So maybe we just happen to get 200 students who would have performed poorly and a little under average in the old model anyways, right? possible. So what we want, that's why we do a hypothesis test. All right. So let's perform a hypothesis test at the I don't know, what alpha level do you want? You choose. You think 0.05? All right, sure. Sure. So let's do it at the alpha equals 0.05 level. So at 5% level. So what's our null and alternative hypothesis here? Yeah, so again, our null is no effect. Going into this, though, we're not sure what's going to happen, so we should choose what type of alternative? Not equal to 65%. Yeah. So our null hypothesis is that we think it's the same, 65%. Our alternative is that we think it's something different to, not equal to. All right? So that's our first step. Our second step is to go get our rejection region. So this is a two-sided test. So what do we need to do? Yeah, we need to take that alpha level and divide it in half and put half upstairs and half downstairs. So I'm going to take alpha over 2 up there and put alpha over 2 down there. So 5% divided in half. That means I need to put 2.5% upstairs and downstairs. So then my cutoffs are going to be negative z sub 0.025 and positive z sub 0.025. And what are those values? So if you look them up in your table, this is actually going to correspond with the cutoff for a 95% confidence interval. Remember we used z alpha over 2 for our confidence intervals? That was the z value. So go to your table.
Negative 1.96.
Mm-hmm. Yeah.
Positive 1.96.
Yeah, go to your find 0.025 in your table. And boom, here it is, right? 0.025. And what's the z-score? Negative 1.96. Yeah. So the lower cutoff is negative 1.96, and the upper cutoff is 1.96. Okay. So that's our cutoffs. We say if our z-score goes below negative 1.96 or goes above a positive 1.96, then we're going to call it and say, yep, it looks like this program's having an effect on pass rates. All right, so we got our cutoffs. Now what do we need? Yeah, we need to go get our actual test statistic. So it's going to be that p hat minus p0 over the square root of p0 times 1 minus p0 over n. And then p hat was, in this case, 60%. We're still working with a claim of 65%. And we use that claim as our downstairs. And now this time we took 200 samples. All right, so try that out. Take a couple seconds or a minute. Calculate that z-score, and hopefully 2 or 3, 4 of us can agree on one, and you guys tell me what you get. You can do it all in one step if you want.
So the P0 is the null hypothesis?
That's right. P0 is the claim, yeah, or the null hypothesis. Because remember, we're assuming the null is true until we prove otherwise. So we're treating that P0 as the true proportion until we have enough evidence otherwise. So what do you guys get for a z-score there? It's going to be negative 1 point something maybe? I have no idea what it is. Negative 1.48? Negative 1.48? I got 2. I think I got 3 people that said so. Okay. So your z-score is a negative 1.48, right? So now we got to go make our decision. So we set cutoffs at negative 1.96 and 1.96, saying our rejection regions were out here. Where is our statistic? So, you know, inside is the acceptance region, basically, if outside is the rejection region. So are we in the acceptance regions or the rejection region? Right. So then we'd say, okay, 1.48 is not in our rejection region. So what should we probably do? Accept it. It's kind of weird. We use weird phrasing, but we would say we fail to reject. We can't reject it. And the only reason we do that is because it's not like we're saying it is true. The null is true for sure. We're just saying, as far as we know, it looks like it could be the case. That's what we're really saying, right? So there's your decision.
It's just a way to cover yourself.
Right. So then we could interpret that. The interpretation, remember we put the level. So at the alpha equals 0.05 level. And then was there enough evidence or was there not enough evidence to suggest the alternative? There's not enough evidence. There is not enough evidence to suggest that the new program pass rates are different than 65%. Or in otherwise, looks like there's no effect. Yeah.
Okay, is it just because it's like common sense we know that there's not enough evidence, or like why do we exactly know that there's not enough evidence?
Because so remember were you here yesterday? I can't remember.
No.
Okay, so eventually, were you here Thursday?
Yeah.
Yeah, sorry, I wasn't here either yesterday, but good point. But were you here Thursday?
Yeah.
So remember we talked about the car and like the miles per gallon, and then eventually you have to make a choice, right?
Mm-hmm.
So eventually you have to make a choice and say whether you believe them or not. When you make that choice, you can't ever be sure you're actually making the right choice, right?
Yeah.
It's just like in a jury trial. But eventually you have to make a choice. Do you believe them or do you not believe them? So we got to make a cutoff. So then the way we do it is we make the cutoff using our alpha level.
No, I get that.
And the
but it was, like,
statistics.
in the cutoff, so I don't.
Well, so remember, our rejection region is outside. Our rejection region is always outside. So our rejection region is always above or below the cutoffs. And so here, we would have rejected if our z-score would have been above 1.96 or below. And we got those based on our alpha level. So ours is inside. So we shouldn't, since it's not out there, we shouldn't reject. We should fail to reject. Right? But what is the null hypothesis? The null hypothesis is 65%. Right? So the null hypothesis is 65%. The null hypothesis is no effect, basically. Right? And so we're saying, as far as we can tell, don't reject that. Don't reject that it's not this null hypothesis. So it looks like the truth could actually be 65%. In other words, it's ineffective.
But that's only because it was in the accepted.
Yeah, only because it was in the accept region.
Okay.
It's basically we were in this region where you should accept the null hypothesis. Accept the null hypothesis, which was no effect.
So my brain is like
No, I
reversing
understand.
this around.
I don't know. I get everything you just said. I just don't get like evidence, like why we use the word there's not enough evidence. It's okay. We can talk about it later.
It's yeah. Well, we're like you guys can go if you want, but the reason is here it's the way we phrase it,
Okay. Maybe that's what it is. Just the wording.
and it's not even that important. I mean,
Okay.
the moral of the story is we didn't reject the null hypothesis, which means we're basically saying 65% looks like it could be true. Yeah, this is sort of technical gibberish. Maybe it's not that important to phrase it that way. That's why in parentheses I put down here.
I get the math part.
Yeah, that's why in parentheses down here I put it looks like no effect.
Oh, I wasn't here on Thursday. Can I get my test?
Yeah, I got it in my. You'll have to come to my office to grab it.